Good afternoon, ladies and gentlemen, and welcome at the SAIEE Free State Centre webinar. We will be discussing today an optimization-driven declarative framework and its power applications. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other. However, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the Events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so ensure you check back as often as possible for new uploads and subscribe to our YouTube channel. It is for free. A certificate of attendance will be issued a few weeks after this webinar once we have received the CPD validation number from EXA. I'd like to introduce you now to our host for this afternoon is Joseph George, the chairman of the SAIEE Free State Centre. Joseph is currently working as a senior electrical engineer in the Department of Public Works and Infrastructure in the Free State. Previously, he used to work for Eskom as a field service engineering and a network planning engineer. He has more than 10 years of experience in electrical infrastructure planning, execution and design, specializing in renewable energy design. I hand you now over to Joseph.
Thank you, Minx. Welcome everyone to our June technical talk here in Free State Centre. Just a couple of things I want to go over. If you have any questions, you'll see here on the panel there's a question chat box. So just post your questions there, and then at the end of the presentation, then I will go through the questions for Lesiba. Right. Without further ado, our speaker today is Dr. Lesiba Mokonyana. Dr. Mokonyana is an electrical engineer and a researcher developing software to design and operate distributed energy systems. He received his PhD in electronic and electrical engineering from the University of Strathclyde in the UK, where he focused on developing mathematical optimization models of active network management and hosting of distributed energy resources. Before Strathclyde, Lesiba was a network optimization engineer at Eskom, having received his B.Eng honours and M.Eng in electrical engineering from the University of Pretoria. The topic for today that Dr. Lesiba will be presenting is an optimization-driven declarative framework and its power applications. Many problems in power systems and energy management are naturally modeled as optimization problems. However, practitioners often find it challenging to maintain reliable implementations. In this talk, Lesiba will describe recent advances and the impact on the composability and extensibility of the recent and classical applications, including optimal power flow and electrical vehicle charging. Lesiba, I'll hand it over to you.
Can you hear me, Joseph?
Yes, I can hear you, Lesiba.
Great, thanks, Joseph. Hello, everyone, and thanks for joining. I'll be talking today about an optimization-driven declarative framework and its power applications. Oops. By an optimization framework, I mean, when you solve a problem, you state what it is that you want to achieve, but not how to get there. Sorry, I just want to turn on my webcam. Can you see me?
Yes, we can.
All right. I'm just gonna minimize. All right, I'm gonna continue. Sorry about that. All right, by an optimization framework, I mean, we state what we want to achieve, but not how to get there. So when you solve a problem, you say what it is that you want to solve, you feed the problem into a solver, and then the solver returns a solution. These optimization methods must be actionable. By actionable, I mean they must obtain reliable solutions in reasonable time or at scale, and preferably using open source solvers. Okay. I will go through what makes it a good time to apply optimization today. Then I'll define what an optimization problem is, just so we're on the same page. Then I'll go into the different solver technologies. Then I'll give a few examples before we conclude. So what makes it a good time today to apply optimization? For one, there's improved computational power. Computers today are vastly more powerful than computers decades ago. You only need to look at your phone to see how powerful they are, way more powerful than computers decades ago. Secondly, the algorithm advancement. I should point out here that this is the work of many people over many years, and I've only contributed just a tiny bit to the research. The algorithms that we've seen advance greatly over the last few decades are interior point solving and operator splitting methods like ADMM. And we've also seen a rise of reliable open source solvers. Thirdly, we have really good languages that are free to use. These include Python and my favorite, Julia. These languages also have automatic differentiation, which can be crucial to optimization. With automatic differentiation, when you specify your function, you do not need to worry about also specifying its Jacobian or its gradient. They also have domain-specific interfaces. These include domain-specific languages like CVXPy, which I'll go into in a bit. Let's first define what an optimization problem is in its canonical form. So in an optimization problem, we minimize a function subject to its inequality constraints and equality constraints. So in this problem that you see on the screen, x is a variable and bi and ck are constants. For a convex problem, the functions f0 and hk are convex, and fi is linear, meaning that fi minus bi is affine. Otherwise, the problem is non-convex. This makes a great difference when you're solving complicated problems. If the problem is convex, then it means you could solve it way faster than when it's non-convex. Let's look at the different solver technologies. So I'm just going to crudely go into the solver technologies using a timeline, but it's actually not how it actually is. What happens is they've developed in parallel really over the years. So firstly, what we've witnessed is that before you could make your own solver. That is, you'd have your problem formulated, then design a custom solver to solve that problem. This exploits special structure, but could take a lot of effort and could be hard to generalize. We also had proprietary general purpose solvers. So we've also had proprietary general purpose solvers, which had standard problem formulations, meaning that when you specify your problem, the specification has to match the solver's notation. Examples of these can be found in MATLAB, Cplex, MOSEC, and others. In recent years, we've seen the rise of well-tested open source solvers. So just like before, you formulate your problem, but the problem has to match the solver's notation. Implementations of these include GLPK for linear programming, CLP for linear programming again, and then IP-opt for nonlinear programming, and splitting conic solvers for convex conic programming. And then now, what we have is a democratized approach. With a democratized approach, you have domain-specific languages. So these accept generalized problem formulations, meaning the user can specify the problem in a form they understand. The domain-specific language, or DSL, will translate the problem into a standard form that matches a solver's notation. And then take the problem, feed it into a solver, which could be an open source general purpose solver. The solver produces a solution, and then the DSL translates the solution into a user recognized result. This means the details are abstracted away. This approach makes optimization more accessible, as you'll see in a bit. We can quickly modify the problem's objective and constraints. It is straightforward and user-friendly. Implementations of these include AMPL and GAMS, which have been in existence for decades. Newer DSLs include CVXPy, PyOmo, and JUMP in Julia. Let's look at a DSL modeling example. So the user can specify, let's say, a quadratic expression, which could be an objective, in a DSL. The DSL can then take the expression, feed it into one solver, which could take a vector form of a quadratic function. But then if a user is looking to use a different solver, which uses a least squares form, the DSL can automatically convert the user's specified expression into the least squares form as well. We're now gonna look into a few applications of optimization. Let's first have a look at the optimal power flow. This problem was formulated in 1962 by Carpentier, as far as we know. The DC model, which involves linearization, is widely used around the world. But what we're going to have is the full AC optimal power flow. The problem has the complex bus voltages, complex power, and the controls are generation, demand, and switching. The objective that we have is we need to minimize the cost of generation, but there are many other costs that one can use, such as minimizing curtailment, minimizing losses, or even tracking. What makes this problem quite challenging are the AC power flow equations. The AC power flow equations involve nonlinear functions of voltage. These can be quadratic polynomials or trigonometric functions. The problem also has inequality constraints. These are the voltage magnitude, angle, and thermal limits. Just to give you an idea of the progress that has been made over the last few decades, I can solve the OPF problem for a 4,600 bus system on my 7-year-old computer using IP-opt in about 80 seconds. We're now going to have a look at the multi-period ACOPF. We're going to solve the multi-period ACOPF for a network with 300 buses, 69 generators. The generators include 11 renewable energy generators, plus 3 storage sites. This problem has linking constraints compared to the static OPF. The linking constraints can be the state of charge evolution, energy curtailment, and this problem is solved over 96 15-minute intervals. We can solve this problem in about 7 minutes. That's using, again, my 7-year-old laptop. Let's have a look at the PV and wind generation profiles. Here, I just wanted to show you that you could use many different profiles and not have to worry about how you'd handle them. So we do not need a set of rules to control these generators. What we need to do is specify exactly what we want, specify it as an optimization problem, feed the problem into a solver, and wait for a solution. These are the load profiles on the network. After solving the multi-period ACOPF, we get the following profiles for energy storage. As you can see, I did not need to develop a set of rules to get the storage profile. I just specify the problem, fed it into a solver, and this is the solution I got. This is just one of the constraint branches on the network. There are times at which the feeder is constrained, such as the intervals around, well, interval 70, and then the intervals before interval 6. As you can see, the OPF restricted power flows to the capacity of the branch. Next, we're going to have a look at building energy management. In the building energy management problem, we have load, which in this case, we just assume it's not controllable. We have PV generation, which can be curtailed if necessary. We have energy storage, and we also have power from the grid. And I must say that in this problem, we include load shedding just to reflect what's happening in SA. This problem has the following variables: grid power, PV generation, storage power, and the battery state of charge. The objective is to minimize the energy cost using a time of use energy price. The constraints are the power balance, which includes load shedding, the state of charge evolution, storage power bounds, and storage energy bounds. Let's have a look at the results. So this problem can be solved in about 4.3 milliseconds if you're looking at 24 hours. And then you get about 320 milliseconds if the problem has tricky constraints to satisfy. You can also solve it in about 38 seconds for 8,760 hours. That is about 1 year. But if the problem has very tricky constraints, you can solve it in 5 minutes for a whole year's profile. And these are the profiles that you get for grid power, PV, the load, and then including the energy price as well. As you can see, we get the following battery profile. But again, you do not need to worry about the rules or not satisfying constraints because we do this upfront. We say what it is that we want, and we let the solver produce a solution for us. The problem, let me just, I forgot to mention, there's load shedding over the intervals 6 and 7. You can see that over those intervals, the battery is discharging. Now, if we change the load shedding intervals to interval 20 and 21, we'll see there's a change in battery profile as well. The grid supply also changes. Next, we're going to look at our final example, reconfigurable EV charging. In this problem, we have 3 types of chargers. We have fixed AC charging, we have fixed DC charging, and we also propose a reconfigurable charging system. This system is meant to minimize the number of fast chargers you have. But the difference is that you also have switches to reconfigure the charging paths between the EV and the chargers. The variables in this problems are control states of EV charger switches. The objective again, is to minimize the cost of energy with a time varying energy price. The constraints are one charger has to charge one EV at a time. We also have a battery charging characteristic, which involves constant current charging and constant voltage charging. We also have user inconvenience constraints. This just means that there are certain users who are flexible, so they can park their cars for longer than they had planned to. So if they do that, that means we could change our charging profiles based on their specifications. And then the last constraint is the temporal grid capacity. Here it just means that the transformer capacity changes over time because there are other loads connected to the transformer. Let's have a look at the results for workplace charging. So this is for the charging of 50 EVs using 5 DC chargers or fixed AC, meaning you have dedicated chargers for all the cars. For this problem, you'll see that for an uncontrolled AC charging system, the red line, you'll see that there's a violation of the transformer capacity. And then when we use DC charging, but uncontrolled, it violates the thermal constraints massively as well. But if you control the charges, reconfigure the charging paths between each EV and each charger, then we can control it in such a way that we satisfy the transformer capacity constraint. I should also point out that with this approach, reconfigurable charging, we have a 10-year NPV of about 2.16 million Rand with control DC charging, and then about 1.6 million Rand for fixed AC charging. So that just shows the attraction of using a reconfigurable system. And that's all for our applications. To summarize, open source DSLs and well-tested solvers, those are open source solvers, improve productivity and I think make optimization accessible to engineers. Challenging problems are now amenable to optimization. And as you've seen from the examples, we have many optimization problems that can be solved at speed and scale suitable for practical applications. And that's all, thanks. And I'll be happy to take any questions. Thank you.
Thank you, Lesiba. Penyo asked a question. He says that in the Northern Cape operating unit in Eskom distribution, we've seen a lot of LV connected PV generation. Which solver would be best suited to do optimization for such a network? Lesiba, we can't hear you.
All right.
Right, yeah, we can hear you.
Can you hear me now?
Yes, we can.
Cheers. Yeah, thanks, Penyo, for the question. Yeah, all you need is the multi-period OPF. It depends what you're trying to achieve for controls. You could use like OPF that focuses on curtailment, but let's say under special conditions. So maybe you have N-1 contingencies, and you have no other way to control your flows. So you could use OPF, minimizing curtailment as your objective. But there are many other ways to do it. So you could also, like demonstrated in the example, you could also install battery storage and control it again using OPF. So it really just depends on what you have, what are the actuators you have, and then we take it from there. But I believe the multi-period OPF should form the core of how we solve the problems in industry, or in this case, power networks.
All right. Thank you, Lesiba. Are there any more questions from you guys? If you do, please post in the question panel here on the right. I'm not seeing any more questions. Thank you, Lesiba. Thank you very much for your presentation. I really enjoyed it.
All right. So any other questions? I think yeah, if anyone has an application they find interesting and maybe you wanna go into it, and here if optimization could be a suitable approach to solving it, they could yeah, just let me know and I'll be happy to chat about it.
Fantastic. Okay, we'll put your email up. We'll put your email up, so if anyone has any further questions, they can email you. And thank you, Lesiba. Thank you for taking the time out to talk to us. And Minx, over to you. That was the last question.
Thanks, everyone. Cheers.
Thanks, Lesiba.
Thank you, Joseph. If anybody has questions for our presenter, please reply to the email or just send it to Minx, M-I-N-X, at saiee.org.za or Free State Centre at saiee.org.za, and we will get the questions to our presenter. Thank you very much for joining us today. Thank you, Lesiba and Joseph, for your time. I appreciate that. And hopefully we will get to host you all soon again. Have a good afternoon. Goodbye.